Uh, okay, everyone. Today, my presentation focuses on the information hidden by the isotopic composition of global basalts in high-dimensional space. This presentation is based on Stracke's paper from 2022 and as well as some related paper. Before discussing this paper, I will give a brief introduction to the authors and some basic knowledge about mantle geochemistry. Andreas Stracke is a professor from Wilhelms-Universität, and he's an expert in mantle geochemistry, including the mantle heterogeneity, the interaction of mantle with other reservoirs, melt generation and evolution, and also the analytical techniques and quantitative tools for mantle geochemistry. So now that we are discussing about the mantle geochemistry, I'd like to share some common perspectives on this subject. Generally, geochemists use three ways to investigate the mantle composition. The first is the theoretical models. The second is through experiment. The third is analyzing the chemical composition of rocks directly. And they usually use peridotites and basalts. So if we got some basalts, we could analyze their major elements, trace elements, and isotopes. And today, my presentation only focuses on the isotope of basalts. Previous studies have examined the isotopic composition of global basalt in 2 or 3D space. And in the 2D figures, they found some basalts with extreme isotopic compositions, and thus they defined 4 end member termed DMM, high-mil, EM1, and EM2. They also found an area where the majority of data overlap and forming an area with highest data density. So the prima, namely the prevalent mantle, was given to this area. And in 3D space, Hart in 1992 found that the isotopic arrays focus on one area and they called it fossil. So previously, the geochemists defined several end members to encompass an area that could cover all the data sets and describe their distribution to further explain the genesis of basalts. However, these studies are limited to the low-dimensional space, and Stracke in 2022 re-examined this data under 6D space. His team compiled 2,744 oceanic basalts with their radiogenetic isotope composition. And this is the 2D figures of as a projection of 6D space. And we can find the similar structure to previous study that 4 components encompass an area that could cover all the data sets with an area called prima with the highest data density. Then they use the TSNE method to accomplish clustering, dimension reduction, and visualization simultaneously. The advantage of TSNE is it could preserve high-dimensional local data structure in low-dimensional figure. We can find that by tuning the hyperparameter called perplexity, we can find the 2 clusters discrete in high-dimensional space could also show the similar pattern, and the parallel structure. Yes, this hyperparameter should adjust and to reveal the true structure. And also the intersected structure. So based on this advantage, and we can catch a glimpse on the data structure of isotopic composition in high dimensional space. And this is the result of the TSNE method, and we can find that, and Stracke divided the basalt into 15 groups, and within each group, they share the affinity in isotopic composition. And the data structure of this figure shows that the 15 clusters are separate, and we can deduce the similar structure in high dimension space. So it proves that the overlap of isotopic data do not exist. And further, the geographic distribution of these clusters shows that these clusters also shares the regional affinity. And so Stracke delineates 15 regional domains. Within each domain, the isotopic composition of the basalts will significantly influenced by the regional geodynamics. Therefore, this paper comes to conclusion that the overlap of the data set in 2 or 3D space, the prima does not exist in high dimensional space. And the geographic distribution of this data shows that the regional geodynamics exerts significant influence on their composition, and their genesis could not be simply ascribed to the mixing of different members. And this paper will give us some further implication. And this conclusion the second conclusion is not so surprising, that the actual composition of the mantle salts could be more complicated than we previously imagined. In 2021, Stracke proposed a theoretical model that in this figure, the upper part of this figure shows the simplest model, that the morph source is made up of ultra depleted mantle and the fertile mantle. By adjusting the proportion of the two components, and the isotope composition of the basalt will change a lot. Not even to say the lower part, that the oceanic crust recycled back to the morph source. And as a matter of fact, there is some case study that could prove the Stracke's model. That Wilhelms in 2022 had published the paper in Science Advances, and he found some prototypes represent the ancient cratonic mantle in southwest Indian Ridge. And his observation is also supported by the numerical simulation that if a plume impinged the bottom of the cratonic lithosphere, the lithosphere will be disintegrated, and the prototype will be transferred to the morph source, and it will introduce more complexity to the morph source. So in conclusion, these studies give us two implications. So if we try to catch the global trend from the global data set, two things should keep in mind: that we should use as much high dimensional data as possible to avoid being misled by low dimensional data, and the regional effects on the results should be excluded before asserting the trend we observed is the real global trend. So that's all I want to share today. Thank you, and let's go for discussing.
Okay, thank you.